I've already told you when you have to have them done.
Oh, he started capture.
Yeah. All right, so this unit is about intermolecular attractions and about gas laws. We'll get to gas laws a little later. Right now I want to talk about intermolecular attractions, okay? So when you were in physical science, you learned about how atoms bonded together in a real simple way. You learned about either covalent bonding or ionic bonding. Okay? And your covalent bonding was you learned probably about, they were sharing electrons. And ionic bonding was giving up and gaining electrons, perhaps. Okay, opposite charges. What we're going to do is we're going to take some of this and think about it in a little bit different way. In ionic bonding, you've got particles that have a positive charge and particles that have a negative charge. Okay, so this particle attraction is what holds an ionic compound together. Okay, well, when we're talking about covalent bonding, mostly we're going to look at the whole molecule. So after all these molecules have actually already bonded together and shared electrons, they have overlapping orbitals and overlapping electron clouds, we're going to look at how this molecule is attracted to the next molecule. Okay? We're not looking at the bonding or the attraction between this atom and this atom when we're talking about interparticle attractions. We're talking about this molecule being attracted to this molecule and by how much and how that affects the overall material on a larger scale. Okay? So with ionic bonding,
so like what state it's in?
Like how it affects what state it's in. Okay? So with ionic bonding, you've got all these negative and positive charges, and they don't just stop with two. Okay? This positive charge particle, and it might be 2 or 3 positive, okay, is attracted to this negative one, and that's attracted to this positive, and so forth, and you get these really large structures all kind of stuck together in a crystal, at least when it's not in water. Okay? Well, the attractions between this molecule and this molecule are weaker by comparison to this, but nevertheless, they can do some pretty big things once we understand what they're doing. So it's not just a matter of it's weak, doesn't do much. It's weak, but when you get a lot of them together, they can do a whole lot. Okay? And then there is a kind of structure, too, that kind of falls outside of all of this in terms of covalent bonding, where you've got a particle that is covalently bonded to the next particle, and it goes on in a continuing structure like this. And I'm doing it only two-dimensionally, but it really happens three-dimensionally, like a diamond. Okay, and that's all covalent bonding. So with something like a diamond, you have this interlocking structure that continues on and on and on, covalent bonding, and it will make a very strong particle when you get or chunk when you get it done. So these crystals, which are all covalent bonds, actually end up on the whole being stronger than these crystals. Okay, these can be split a little more easily between the charges than this can. All right? All right, so what we're going to be looking at, and you kind of know about the attraction between these particles. You kind of know about those. You know they're attracted to each other. We've already talked about them being separated, those charged particles being separated when you're dissolved in water. Some are aqueous and some aren't aqueous. So something like sodium chloride, if we put it in water, you should already know it separates into separate sodium ions and chloride ions. And those are aqueous because they're actually dissolved in water. Okay? All right. So it is possible to separate those. Now, with covalent bonding, there are attractions between particles, and what we're going to spend a lot of time in this unit looking at is how they get attracted, because it's not so simple and straightforward as these positive and negative charges. Now, in a previous unit, we did look at molecules that have a partially negative side and a partially positive side, like water. Okay? Remember, water was, you had your two hydrogen ions, and you had hydrogen atoms covalently bonded to an oxygen atom, and the oxygen atom is more electronegative, so that's more electronegative, and these are more electropositive over here. Okay? So this is a polar molecule, where overall then, this end is partially negative and this end is partially positive, making it polar, two poles. Those are called dipoles, because you have two poles. Okay? Dipoles. And so, just as a general representation of a dipole, I'm just going to draw one sphere here with a positive and negative end to represent any kind of molecule that has a permanent dipole. So polar molecules, just let us talk about terminology here for a minute, have something called a permanent dipole. Okay? And anything with a permanent dipole, anything that has a permanent dipole.
Is it permanent?
Huh?
A.
Oh, yeah, it is, isn't it? Okay. A permanent dipole. Yeah, that actually somewhat means something else, doesn't it? I forget what it means. Anyway.
Permanent? Like
Yeah.
a permanent marker. Do you have a dictionary?
It doesn't matter. It's all right.
Permeable.
I forget. All right. These permanent dipoles then are attracted to each other, and we know that water molecules are attracted to each other.
Yeah, yeah.
Okay, at least you should know it now.
Yep, we do.
Okay. So if I have molecules that have no permanent dipole,
Ooh.
they don't have this positive negative thing.
Right, right.
Okay. There's really no partially negative or positive ends on that molecule to hold on to this one. Okay? That doesn't mean there isn't any stickiness. All molecules have stickiness. All molecules have some kind of stickiness, and we'll get to that.
What about slippery ones?
Even slippery ones have stickiness. Okay? But if I have this molecule and it's anywhere near another molecule of the same type, well, they're attracted because of that opposite polar attraction. And this kind of attraction is called a dipole
Right.
attraction. Dipole.
Dipole.
It's-
Oh,
Okay?
why is it called that?
You got a molecule with a dipole and another molecule with a dipole. Dipole attraction.
What would it be like a... Okay.
Tom, you're a genius.
Okay?
Thank you, Tom.
Attraction. Dipole attraction. So water has one of the strongest dipole attractions. Okay? In fact, water has roughly the same mass. Water molecules have roughly the same mass as carbon dioxide. Carbon dioxide is nonpolar. If you remember when we did the structure of carbon dioxide, we found that because the oxygen atoms are at 180 degrees from the central carbon, they cancel out any polarity in the bonds. Remember that? You don't remember that?
I remember.
Okay.
Tom does.
All right.
I'm a cougar with bare hands, you better watch out. Man.
So get out your test references and let's look at your electronegativity, periodic table of electronegativities, and remind ourselves about this, because this is really important that you can draw in the information we learned in, I guess it was Unit 4, when we learned how to figure out whether molecules are polar. That's really important that you can do that, and you might need to go back and review that unit where we learned about polarity. Okay? So get out your test references, please.
References coming up.
References. It is very important that you try to keep in mind the material you learned in earlier units. They keep coming back on us.
What are we looking for?
Periodic table of electronegativities.
Okay.
You don't? Well, I gave it to you. What'd you do with it?
Is it like at the top of the paper or something?
No, it's in your set of test references.
Oh, I do have that sheet. Jeez, it's the polyatomic anide.
It's on that same sheet, yeah.
Oh, it's on that sheet. Yeah.
Sounds like everybody needs to go back and study Unit 4. Okay, I don't have time to go back and review all of Unit 4. All right, so carbon has an electronegativity of 2.55.
Right.
Oxygen has an electronegativity of 3.44. So if we subtract 2.55, and this 3.44 is the electronegativity for oxygen. We're going to subtract the electronegativity of carbon. And let's see.
9, 8,
0.89.
189. There you go. You got
And that's the electronegativity difference for a bond between oxygen and carbon. So the bonds between oxygen and carbon is polar. So it tends to go in that direction. All right? And then this bond is also polar.
Yep. So it goes in that direction.
Yes.
Like
But because they are equally spaced around this central carbon, this is 180 degrees.
Yeah.
How do we know that?
It's a straight.
Because they are
Protractor out and find out.
they are following this thing we call VSEPR. Remember VSEPR?
Yeah.
Valence shell electron pair repulsion.
Yep.
So the electrons in this bond are repulsing the electrons in this bond. Okay? And so to be as far apart as they can get, 180 degrees fits the bill. And we know that it actually behaves that way because of the kind of research that's been done on molecules like this. And that's way beyond the scope of this class. I really don't have time to go in depth into that. Not that I even can recall it. I have to go look it up myself.
Our scope
Okay.
isn't very long.
Well, you're just kind of beginning.
Well, we can't really. We can't really tell
Hmm?
anything. Nothing. Real talk.
What was that?
Yeah.
All right. So what we're doing is a very simplified way. We learned a very simplified way of determining polarity of molecules using this process. Polarity is far more complex than this one simple idea we're going to deal with in here. But this is probably the most important idea, this electronegativity difference. Okay, now, so if you don't remember that, you need to go back and figure that out, because in this unit, you're going to have to be able to determine whether molecules are polar again, and use that when we're talking about what's happening with interparticle attractions. Okay,
Right.
so carbon dioxide, back to what I was originally talking about, carbon dioxide then is nonpolar. Okay, because whatever amount of electronegativity there is in this direction is being opposed by this. So what's happening with electronegativity is the electrons tend to spend more of their time over here with the oxygen. The definition of electronegativity is a relative measure of how hard one atom pulls on the electrons that it shares with another atom. Okay, so since oxygen is pulling more on those electrons and more strongly on those electrons, like a tug of war, the electrons are spending more of their time over here than they do there. Okay? This is like the popular house in the neighborhood. The kids tend to spend more time over there. Okay? Right?
So all the electrons on the left and right side will pull.
Say again?
All the electrons on the left and right side will pull.
Well, the electrons that are being shared between oxygen and carbon are kind of, the electron density in the center is lower, the electron density on the outside is greater. Okay? The electron density. That means that the number of electrons per unit of space is greater over here than it is in the center.